This is a makeup recording for day 4 of Sci Virtual Circuit Lab Advanced, where we started talking about transistors by discussing semiconductors, PN junctions, doping, MOSFETs, and all that fun stuff. So, to motivate this, we first mentioned that our goal for the remainder of this course, from lessons 4 all the way to the end, is to build up to computer architecture, to understand how a CPU actually works. What is this program counter? Accumulator, ALU, what are these instructions? Why do we have to decode the value in a memory cell to an instruction? What even is a memory cell? And to be able to say, this is what I see in the CPU, but this is what's happening at even the semiconductor electron level. So we're gonna build it from the ground up. And that's our end goal. And we're gonna, on the final day of the class, do sort of a challenge where you are given a task like adding 3 numbers as you see on the screen, and you have to use the fewest possible memory cells to accomplish that. So that's where we're headed. Now, we need to start for any of cool discussion about computer architecture by building up from semiconductors. So all materials have atoms. We hopefully know this. And these atoms have nuclei and electrons. The electrons are things that we care about for electronics, right? So in conductors, the electrons can float and bounce around. In insulators, the electrons are stuck, right? So in a conductor, the electrons are free to, in a conductor, the electrons are free to move around through the solid, whereas in an insulator, they can only just vibrate in place, basically. And a good demonstration of that is this here. So this is an insulator. You can see even if I increase the temperature, things just wiggle more quickly, right? But for a conductor, higher temperature means you have a faster rate at which the electrons are moving around. And when you apply a voltage, you get a current, right? The electrons flow in a particular direction. For an insulator, there's no electrons flowing around. It's all just wiggling, right? So you can't get current in an insulator, but you can get current in a conductor. Now, semiconductors can act like both conductors and insulators, and they're defined by having a close valence band to their conduction band. So I'll go back to this diagram here. In the conductor, all these electrons are free to move around. So we call that conduction, okay? All the electrons are in the conduction band, or the electrons that are moving around, I should say, are the conduction band. In this insulator, all the electrons are just stuck in place. And notice they're forming the bonds between these atoms. So that's one way of thinking about it. And you can call that the valence band of the material because they're all essentially in the valence orbitals of each atom. And so the question is, why in some materials do we have electrons in the valence band? And why in other materials do we have electrons that are also in the conduction band? And the answer, you can think about it with the logic of the Fermi level. So this gets into solid state physics and some interesting things there. But this is a simple enough way to think about that without getting into the weeds of the math. Essentially, when we think about the Fermi level, we're saying if I add in electrons to a material one at a time, the electrons will each occupy a state. And those states will go from low energy to high energy. We'll fill the lowest energy states first, then we'll work our way up to the higher energy states. So you can see what I'm doing here. I'm going to add in electrons, and I'm going to keep doing that. And as I add in electrons, I reach higher and higher states. So at this point, all the electrons I've added are still within the valence band, right? But if I add in some more electrons, we start to fill in the conduction band. And so these electrons are the ones in the conduction band are the ones that are free to move around. The electrons in the valence band are the ones that are kind of stuck in place, okay? And depending on your material and how many electrons there are in your material, the Fermi level will be at a different place. And this Fermi level is largely what determines, okay, am I in the realm of conduction or am I in the realm of insulation? Okay. And particularly for materials for which these two bands overlap, you can see you don't need to get as high energy to reach the conduction band. That's why in these band diagrams, we draw conductors or metals as having overlap between the bands. and insulators having a big gap between them. There's more to it than this. I'm hand waving, and I'm sure there's many questions that remain. Um, but this is just a model for thinking about how why we use this terminology of bands. Now, in a semiconductor, this band gap is tiny. And the reason that's important is because just the energy that's available at room temperature is enough to kick a small number of electrons from the conduction band from the valence band into the conduction band. It's a very small number, but it's an important number. So most of the time, at zero temperature, a semiconductor acts like an insulator. But as you increase the temperature, more electrons are being promoted from the valence band to the conduction band, meaning that more electrons are available to conduct. What promotion means in this sense, take some nuance to think about, and I encourage you to to brainstorm about that. So now, so yeah, the moral is that semiconductors are like insulators, but thermal energy unlocks their ability to act like conductors. Now, let's talk about doping. Or actually, before we do that, let's go back to the demonstration here. So this is what you can ignore the positives, those are holes. We'll talk about that in a second. This is a semiconductor at very high temperature. You can see there's a good number of electrons floating around, right? And so when I apply a voltage, I get current flow. If I decrease the temperature, there's going to be fewer things floating around. So it can still conduct, but to a lesser extent. In other words, this material at low temperature has higher resistance than the material at high temperature. Okay. So let's talk about doping. So doping is the process of replacing silicon in a material with a different atom. So normally, just a blob of silicon is a bunch of nuclei that are all bonded to each other, right? Exactly like a lattice of carbon. So I can keep drawing these bonds out and so on. But we might be interested in having more positive charges available or more negative charges available. And to do that, we dope the material. Doping is literally replacing one of these silicon with a different atom. In doing so, we can either introduce extra group 5 elements or extra group 3 elements. These are from the periodic table. If I introduce extra group 5 elements, you can imagine I have a silicon, and maybe a phosphorus right here. This phosphorus has an extra proton compared to silicon. So it's going to be an extra positive charge stuck in place right there. But it also contributes an extra negative charge. So while you might have one negative charge surrounding the silicon right here, here, and here, you have two negative charges right there. And so that extra negative charge is going to be, you can imagine it as somewhat free to float around. So the doping contributes extra free floating electrons. Because if you squint your eyes in the lattice with the doping, the phosphorus, or in this case, boron, looks enough like the silicon that to the lattice, or sorry, I say antimony. It looks enough like the silicon that to the lattice is just another nucleus. But that nucleus contributes an extra electron that's going to float around. In p-type, it's similar, but instead of contributing an electron, it takes away an electron. We call that introducing a hole, and you can think of that hole like a bubble in water. The bubble is free to float around through the lattice. So, in other words, we've introduced an extra negative charge for n-type materials, and for p-type materials, we've introduced an extra positive charge. But for a p-type material, you have to keep in mind, it's not a real positive charge. It's a hole. It's a lack of negative charge. So don't think about it like a positive charge necessarily. Think about it like a bubble in water, and the bubble can float around in the water. I think that's a better analogy. So as a quick check, if I have a glob of silicon and add some antimony, will this introduce extra free-floating electrons or holes, and will that be n-type or p-type doping? The answer to that question is that you introduce extra electrons because antimony is over here and relative to silicon, it has one more electron that can contribute. It also has another proton, but remember that the proton is nailed in place to the lattice. It's within the nucleus, and the nuclei are fixed in the lattice. Okay, let's now talk about the MOSFET. Or actually, before we talk about the MOSFET, let's talk about the PN junction. So there's a lesson from last year's Sci Virtual that you should go look at. It's on this YouTube channel for understanding why the p-n junction in the depletion region forms. But just to review, if I put a p-type material next to an n-type material, we end up with this depletion region right here where no free charges can float around. If I apply a voltage, you can see if I apply voltage in one direction, the size of the depletion region decreases and we get current flow. So if I apply a positive charge to this region, you can imagine this our positive voltage. That positive voltage pushes the positive charges into the depletion region, decreasing its size in the same way that the negative voltage over here pushes the negative charges into the depletion region, decreasing it from the other side. If you decrease the size of the region enough, it becomes small enough that currents can get through. However, if I increase the size and I have a battery that points the other way, you can think about having a negative voltage here that attracts the positive charges and having a positive voltage here that attracts the negative charges. And so that's going to expand the size of the depletion region. So this is what makes up a diode, right? We're allowing current in one direction, but we're not allowing current in the other direction. Okay? So we're not going to go further into that. There's deeper reasons and are not, but it's a little more nuanced than the picture I just explained. But that's important for understanding the MOSFET. So let's start with a big p-doped slab, okay? And in the corners, let's put two n-doped regions. This red right here, that's a depletion region, right? Between the p and the n, we're going to get a depletion region because there's a p-n junction there. And so no free charges are floating around in this red region. Now, let's add a layer of metal and some oxide. The goal will be to apply some voltage on the metal such that we attract charges or repel charges within the p-doped region without allowing any current to get through. So we do not want current to get through. We just want to create a field and have that electric field affect things within the semiconductor material. That's why we call this the metal oxide semiconductor field effect transistor. It's a big mouthful, but all I'm saying is we have a metal and we have oxide. The oxide is the insulator, and we have semiconductor. Those are the materials involved. And it's a field effect transistor, a FET, because we are applying a field at the metal up here and having that field cause an effect. But we're not having current go through this metal into the semiconductor, okay? We don't want that to happen explicitly. So let's look at what happens when we apply voltages to this material. And it'll be helpful to use this demo to do that. So this is an N MOSFET. So we have a big P-type body. This big slab here is P, this slab here is N, and this slab here is N. And that should be obvious because you have a bunch of extra positive holes floating around in the P material and a bunch of negative N electrons floating around in the N material. So notice that the source is here. So charges are going to flow from the source and they're going to flow to the drain. Okay? From the source to the drain. That's why we use those terms. Here is the gate. Okay? The gate is where we apply that field effect thing that I mentioned earlier. We do something to the gate to affect the material so that currents can flow from drain to source or from source to drain. We'll see which one in a second. But current will not flow from the gate into the material. Current should not flow from the gate to the material either. So let's see what happens when I increase the gate voltage. You can see I start creating a region by applying positive voltage here that's going to push away the positive charges from the p-type material. Okay? And by pushing that away, I keep doing that. I'm going to push away the positive charges more. Eventually, I create enough of an inversion layer. That's what we call this black region here, the inversion layer, that negative charges can leak through. Because remember, what was creating the p-n junction, if I reset, what was creating the p-n junction was the fact that I have a big p-type blob right here, and I have n-type right here. So that creates a p-n junction. But if I apply this gate voltage, then the p-type blob essentially ends right there, whereas n-type is right here. And so then there's no longer a PN junction in this region right here. That PN junction is gone, and so negative charges can now leak through. There's no depletion layer preventing charges from getting through. So as we increase the gate voltage, we allow charges to leak into that region, but there's still no current. The gate has simply opened a region for charge to exist. But then, if I apply a voltage at the drain, you can see that the charges start going through because the charges are going to be attracted to this positive voltage up here. Negative charges go to positive, to remember that. So that's the sequence of events. And to be clear, this is electron flow. And so the actual direction of current flow is in this direction. That's conventional current. Conventional. Okay. So let's just go over that one more time. We start with this situation with a bunch of positive charges floating around in the p-type body and negative charges in the n-type corners. I apply a voltage to the gate to create an inversion layer. That inversion layer gets rid of the depletion region and allows negative charges to float into the body and create a channel. Okay? By creating that channel, I now have a region for current to flow, so that if I apply the drain voltage, current actually flows. If that channel did not exist, and I applied that drain voltage, you can see I'm clicking this button to get it to go, we still don't get current. We need the channel to exist for current to be able to flow. And the gate opens that channel, hence the name gate. It's a gate. If the gate is open, things can get through. If the gate is closed, things cannot get through. And that's exactly the sequence of events here. Just look at the left side of my screen right now. So initially, holes are floating around, electrons floating around. You have a depletion region. The gate voltage on creates an inversion layer and gets the depletion region to go away. And it forms a channel for current to flow. And so then we need to apply a voltage at the drain to get the current to actually flow. Now, we can invert all of that logic to think about the PMOS transistor. This was an NMOS because the thing that was flowing was the N's, the negative charges, the electrons. In a PMOS, the thing that flows is the positive charges, the P. So this is a PMOS. Notice, we now have our body as N-type and our corners as P-type. So I'm going to close the gate. Okay. So now, if I go to a high gate voltage, if I have a bunch of pluses up here, that doesn't actually do anything. If anything, those pluses are going to attract the electrons and make the depletion region even worse to some degree, right? So going to a high voltage at the gate doesn't do anything. Instead, we need to go to a low voltage at the gate. And so if I put some negative charges up here, the negative charges are going to push away the other negative charges and create that inversion layer. So we'll notice the difference here. In an NMOS, you had positive charges at the gate that pushed away the other positive charges. No, I was right. Positive charges at the gate that pushed away other positive charges. In a PMOS, you have negative charges at the gate that push away other negative charges. If you push them away far enough, you create the inversion layer, you get the channel, and that channel is then where current can flow in the exact same logic as we had for the NMOS. But notice, things still flow from source to drain, things in general, right? So here, the thing that flows is electrons. Electrons flow from source to drain. Here, the thing that flows is positive charges, holes, and they flow from source to drain. But because current is the direction that positive charges flow, in a PMOS, current flows from source to drain for a PMOS. For an NMOS, conventional current flows from drain to source, okay? So again, negative charges are flowing from source to drain, so positive charges are flowing from drain to source. Just make sure to keep that straight in your mind. So you should use this tool yourself. I'll have it posted. To use the tools, you literally just download it. So you can see my downloads. You literally just download it and then open it, and it'll open in your browser. You don't need to do anything fancy with an HTML renderer or things like that. And so use these tools, work through the choreography here, make sure you understand that. So you can think of a MOSFET like a sink faucet, right? If the gate is closed, current can't flow. If the gate is open, current can't flow. That's the analogy, right? So the water for a PMOS is going to be the holes, NMOS is going to be the electrons. And we just talked about this. In a NMOS, current flows from drain to source, and a PMOS, current flows from source to drain. And so this is all stuff that we just discussed. Again, just really hammering in this point that in a PMOS, current flows source to drain, and an NMOS, current flows from drain to source. So these are all just review questions. I think there was a Kahoot that we did during the lesson as well. And so that was good review too. So that's all. Thanks very much.